So our goal today is to talk about electric potential. We talked about a little bit of electric potential before we did our electric field mapping lamps. That way we'd have an idea of voltage so that we could relate our measurements to the electric field. We're going to talk about that in more detail now. So looking at the three charge case from when we were talking about potential energy, the potential energy of Q0 was given by this formula, where basically you found the potential energy between Q0 and each of those three charges and added them up. So no matter what you do, there's a part of this that stays the same, no matter what happens. And that is the Qi over Ri. So essentially, if you could remove the test charge from this equation, then we can define the potential essentially at this point right here. And that's what's really cool, is we can define the potential here at this point without actually having to put a test charge in place, which is really fabulous. So that's kind of the goal of electric potential, is to essentially remove the need for a test charge. We did essentially the same thing when we were talking about the gravitational field. We talked about G, which was the gravitational field strength, by dividing out the mass from the gravitational force equation. So that way you didn't have to have a test mass to determine the actual gravitational force. You could just talk about the gravitational field strength. So it's that same kind of idea. We also did that with electric fields. And instead of talking about the electric force between two particles, we divided out the test charge so we could just describe the electric field. So this is kind of a trend that we have here, where we are moving away from that idea of action at a distance, which requires the interaction between two particles, and the fact that all you need are source charges in order to create essentially some perturbation in space. And this is actually really, really important for actually modern physics. The way we describe things is action at a distance starts to fall apart when you start trying to talk about like EM radiation and things like that, relativity and so forth, where Newtonian mechanics doesn't fall in. So by removing out the need for a test charge, you're removing the need for action at a distance and creating just kind of like a field model, which is much better for like everything else that we are going to do this unit. So the electric potential would therefore be the sum of all of the potentials at a particular point. So basically you just add up the potential due to all of these different charges. Potential is a scalar. It's a scalar that can be positive or negative depending on the source charges, but it is a scalar, which means you don't have to do, there's no vectors, there's no vector addition, which is actually going to make things really easy, because we're going to actually do things very similar to what we did with the electric field. You know, we're going to take a line of charge or something like that and say, okay, well, over here at point P, I want to find the potential due to kind of like this whole like line of charges. This was your first derivation packet. And so you're going to take your little dq here, you're going to find an r and so forth. But when we did this with the electric field, the electric field was a vector. So I found like a little dE here due to that little portion of charge, and then it had a dEx and it had a dEy, and depending on what point I picked here, I could have both x and y components, or just an x component, or just a y component. But since potential is a scalar, when I go to find the potential at that point, then I don't need any of this vectors, and then I can just add up the potential at that point due to all of the different ones. So no vectors or anything. And that's the biggest mistake that I see people make when they're doing potential, is actually trying to make potential a vector, and they start finding components and start summing up the components in x and y, and you don't have to do that because it's a scalar. So we can therefore define the potential energy of a given point charge with this formula. So we define potential to be capital V, and it's going to be 1 over 4 pi E naught Q over R. So once again, basically the same thing as our electric potential formula, just without the Q0. Now, be very careful because capital V on its own is potential. If we want to talk about voltage, voltage is actually a difference in potential, delta V. In Physics 1, and you might see a lot of physics websites that are teaching kind of at a lower level, something like Physics Classroom, where they're going to use delta V, like an Ohm's law. You might see delta V is IR, or you might say V is equal to IR. So technically V equals IR is not true. It has to be a delta V. It has to be a delta V because it is actually a difference in potential. It is not V equals IR. In order to have current, you have to have a difference in potential. So just be careful that you don't do that here in physics, that you separate the difference between V and delta V very clearly in the work you do, because it does make a difference. So this equation is derived assuming that your potential is zero infinitely far away. So that is very, very important, because we can actually find potential by setting zero equal to anywhere we feel like. We did this with gravitational potential energy and just said, oh, I'm going to assume that the potential energy is zero at the surface of the Earth, even though it's only zero infinitely far away. So that's where you start talking about like differences in potential. So understand that this formula can be derived just from the electric field, essentially that it is zero infinitely far away. So that is the assumption being made with this equation. So this essentially represents the potential energy that a test charge would essentially have if it were placed at that point. So if you were to actually put that point charge in place, multiply it out, and add that, then that would give you that potential energy. So potential is a representation of potential energy. The units are going to be energy per unit charge, which is joules per coulomb. And that is what our volt is. So some things to remember. The potential is going to increase if you move in the direction opposite to the electric field. That's because that's the way potential energy works. Potential is going to decrease if you move in the same direction as the electric field. So knowing the direction of the electric field is going to allow you to determine whether potential is increasing or decreasing. So here's an example. So we have points A, B, and C. And we want to know what is the potential difference between points A and B. So potential difference would be delta V. So you're looking at the difference in potential. So VB minus VA, because when you're looking at the potential from A to B, you're actually doing the math from B to A. B minus A, end minus start. So that's kind of important. So this is basically saying between points A and B. So you do B minus A. So notice how the variables get switched in how you write that. That's important because that would determine sign. If you switch the signs, you would end up with the wrong sign. But then you could qualitatively fix the sign if you needed to. So here are our options. So pause, take a look, see what you think. When you're ready, start back up. So I'm assuming you've came up with this decision on your own. So the electric field points in the direction of decreasing potential. So since points A and B are in the same relative space, so they're here, we can approximate that they are at the same position, essentially, in this electric field. So therefore, there should be no potential difference between them. Ta-da! All right. So you should have been able to answer that question based on being able to look at the electric field maps that we've done before. Okay, that was kind of our goal. All right, here's another one. Try this question. All right, so the electric field points in the direction of decreasing potential. So the electric field points basically from B towards C. So therefore, C has to be at lower potential. So false. So nice qualitative questions. Like I said, those are questions that you should have been able to answer before. So we're just kind of reviewing here. All right, here's another one. Negative charge is moved from point A to point B. Its electric potential energy will do what? Pause, think about it. Start it up when you're ready. So in this case, if you were to place a negative charge and move it from A to B, because there is no difference in potential, then you would end up with no change in potential energy. So the potential energy doesn't change. Because to get potential energy, you just have to multiply, I guess I'm not sure if this explicitly said this yet, but basically if I want to find potential energy is just going to be Q0 times V. It was implied in some of the other work, but that's actually really, really important here, that potential energy can always be found by Q0 times V. This is similar to the fact that the electric force can always be found by taking Q0 times E, except for the electric force and field are actually vectors, so the vector direction actually matters, whereas potential energy and potential are scalar values. Kind of fun there. All right, here's another one. Compare the potential differences between A and C and B and C. All right. So since the potential at A and B are the same, and we know that C is at a lower potential, there is a difference in potential. But we only have to look at the direction, essentially, between these points. So because going from A to C, I should probably pick a different color. Because going from A to C and A to B go through the same difference in potential, then you're going to end up with the same potential differences between those. All right. So what about relating work and potential? So if we wanted to actually relate work and potential, we know that we can relate work and the electric field. So all we have to do is divide out that test charge, and we can actually find the potential as actually the work per unit charge. So you can find the difference in potential from A to B as being related to this electric field just by dividing out your test charge. Now, notice how this says from A to B. So if I want it to be B to A, so I can do delta V from A to B is going to be VB minus VA. So that's not what I have written here. So what I can do is delta V from A to B is going to be negative of VB minus VA. So if I can add a negative into this, that'll take care of it. So I add that negative over here on this side so that the left side says delta V, and then it's the negative the integral of E dot dl or ds or whatever differential you have. This is often also a dr. So this guy here, I've seen it as a ds. I've seen it as a dr. I've seen it as dx. I've seen it as dy. All sorts of different things. It's basically representing direction. So it really just depends on what you're talking about. ds and dl are the most general because they just represent like a path length. So if I have some wibbly wobbly path length, then I can have either a dl or a ds, just depending on what textbook you're looking at. Whereas dr, dx, and dy all represent very one-dimensional motion. So they don't represent necessarily the motion along a curve as well. So what we end up getting is that dv is equal to negative E dot dl, or dv dx is equal to negative E. Okay, because once again, that's like undoing the integral essentially. So this is one of the most important things that we will define. So E is equal to negative dV dx. This is what we needed in order to be able to do our lab. So we've actually talked about this, but kind of looking a little more in depth about how those are related and where this comes around. So the negative is really important because, once again, this is the change in potential with respect to the change in position. So basically, if your potential is decreasing, that means, because that negative, that means the opposite. So that means your electric field is increasing. So, and the opposite would be true. If your potential is increasing, then the negative says opposite, so your electric field is decreasing. So the electric field points in the direction of decreasing potential. And we're often more interested in the differences in potential, that delta V, because that's what we can actually measure. And it relates more directly to work. But I think, in my opinion, since a lot of what we do is we need to be able to measure things, and we use our multimeter, and our multimeter measures difference in potential, not potential energy or anything else, that's another good reason for that delta V. So here's an example. So once again, pause when you get a chance before moving on. So would you want to move parallel or perpendicular to the electric field if you wanted to have no change in potential? So our equation would be this guy right here. But there's no work being done if you move perpendicular to the field. So therefore, in order for work to be done, you have to move parallel to the field. So, and that's due to that dot product. So remember that the dot product means that we're only going to have work if at least some component is parallel. So therefore, moving perpendicular always means zero work. And we saw that in that other example. Just we didn't put it quite in those same words, where we had like points A and points B. So when we moved from A to B or B to A, that motion, that path is perpendicular to the electric field. So therefore, no work was done. Here's another one. Try this one. All right, so in this case, if you release a positive charge from rest in a region of electric field, that positive charge is always going to move in the direction of the force acting on it. So that force would be Q times E. E would be negative dV dx. So the force would be negative Q times dV dx. So since Q is positive, then that means that the force points in the direction to the opposite of increasing potential. So once again, this negative is creating an opposite. So if we have a positive test charge, if our potential is decreasing, and we have a positive charge, then this means opposite. So our force must be increasing. Or, well, as our force is positive, I guess not really increasing. But the idea is that you're going to move in the direction of that force because of that. So your positive charge is always going to move towards a region of smaller electric potential, naturally. Whereas your negative charge would do the opposite. So your positive charge, because it moves in the same direction as the electric field always moves towards lower potential. So therefore, a positive charge is always going to move towards a region of lower potential. A negative charge has to do the opposite, because when you put in a negative charge here, you're going to get the opposite relationship. So a negative charge is naturally going to move towards a region of higher potential. So you have to be careful of your signs. So just kind of looking at a couple other points. Energy is also sometimes defined based on the charge of an electron. So work can be defined as Q times V, where Q would be our source charge. Our test charge. So that really should be like a Q0. So that's Q0. So work is Q0 times V. But if our test charge is assumed to be an elementary charge, either a proton or an electron, then you get E times V, where E is the elementary charge, 1.6 times 10 to the 19 joules. So since this isn't a unit of work, it's also a unit of potential energy. So EV is an electron volt. You may have seen this if you've done AP chemistry during electrochemistry. A lot of times electrochemistry is done in units of EV, electron volts. So talking about equipotential surfaces again, we've looked at equipotentials before, but basically as long as you move along an equipotential, then you would have no work being done. So this is really important for like reading those diagrams. So an equipotential line is what we looked at, but because it was in 2-dimension, we can only have equipotential lines or curves, because they were curved. But if you had a 3-dimensional space, you could have an equipotential surface. And here's some examples of those. So there's your point charge, which we've seen. This was really fun. This would be a equal charge dipole. And you notice that it's actually got this kind of curved X thing in the center, which is really fun. So if you were to move a charged particle, so if you could like take your hand and hold on to an electron, you could move that electron around wherever you wanted, as long as you traced a path along one of those blue equipotential lines in either figure, then you would have no work being done. But the instant you deviate from one of those equipotentials, you are going to have to do work, either positive work or negative work. So because there's no work being done when you move along an equipotential surface, there is no force, Q times E, along the direction of motion in that case, because the equipotential lines are always perpendicular to the electric field. So when you move along one of those equipotential lines, you are always perpendicular to the electric field. So that's also kind of justification why no work is being done.